Hello friends, welcome to the first video. Um, we are going to actually talk about a problem where we have to find the longest continuous subarray with the absolute difference which is either less than or equal to the limit. Let's take an example here, the similar example that is given on the Leetcode question 1, 2, 4, 7 and the limit is 4, right? So you're looking for a longest continuous sequence where the distance between any of those two elements is less than or equal to 4. Okay, so let's say we can take this 8 into 8 or 8 minus 8. Distance is less than 4. Yes, so that's definitely 1. Now 8 minus 2, distance is 6, is it? So that's not a subarray that we can actually use. How about 8 to 4? Of course, that can't be a continuous array. As soon as you keep going ahead, you can't find any continuous subarray because you already got the number which was greater. So anytime 8 and 2 participates, you are that part of the subarray, that part of the subarray, that part of the subarray will never be the greatest. Now let's say you want to do with number 2. 2, 4, 7. Is 4 and 2 greatest? 4 and 2 distance is 2. 7 and 2 distance is 5. So hence 2, 4, 7 can't also be is also not a valid option. So we are left with now, the maximum distance in this case was either choosing 2, 4 in this case, or we can choose also 4, 7, right? Both of them are less than. So that's a maximum number of continuous subarray, either this one or this one, right? So that's just an example that's given on the Leetcode. So that's why our maximum length of that subarray is uh, less than 4 is basically either this subarray or this subarray. Okay, let's do another example just so that we can understand the problem better. Let's say the next example that's given on the Leetcode is 10, 1, 2, 4, 7, 2. Okay, and what's the limit? Limit is 5. Okay, so let's see what we can do here. So 10 and we encountered 1, so we know any part in this subarray is gonna be not valid, right? This subarray can't be valid because 10 minus 1 is gonna be 9, which is greater than 5. Okay, so now what about this subarray? Can this be valid? A continuous subarray. 2 minus 1, 1 is less. 2 minus 1 minus 4, 3 is less. 1, 7, 1, 7, again, it's more. So basically, you don't have any of those. So this one also you can say this part only is the valid subarray that is less than that any elements any two element distance is less than 5. How about element from 2472 now? So let's say you do 2 and you can do 4 2 and 7 2 and 2 2 or any of those elements, the distance would be less than 5, right? So our maximum distance in this case is this particular array, this particular sub array whose length is 4. Okay, so that's our answer in this case. So now that we understand this problem, and I'm gonna just discard this. Now that we understand this problem, we are gonna try to figure out a solution to it. Now, for most of the problem, I do suggest going towards an approach where you are trying to think brute force approach, right? So let's say this is a new problem to you, you haven't really solved it before. What is the brute force way of doing it? Okay, so let's think about the brute force way. So we are again gonna write our example so that it's easier for us to think the brute force way. Now you could technically think about limit is 5. You can technically think that a simple brute force view would be take first element, start from the first element, and then do the comparison until your limit is smaller and do it for every other element. Not only that, so you're gonna compare 10 with 1, 2, 4, 7, 2, and all the other components you are also gonna compare with each other. So what would be the complexity of such an algorithm? You will having a two loops, n into n, and there would be another loop where you are going to compare each and everything with the other one, right? So you're looking at roughly n cube complexity, or maybe more also. I have to think about a little bit more about this. But this is definitely going to be, super expensive algorithm. Uh, so this is definitely not going to pass our use cases because our number length is going to be, it's too big, right? It's 10 to the power 5. So let's think about what can be a little bit better brute force solution. Okay. So one thing we notice here is if you think like this, you can think that if you can go to any subarray, let's say I took this total subarray, and if I find the max element and the minimum element in this subarray, so that's a trick in this question. Okay, you have to realize this trick to be able to solve this question, but you can realize it by saying for this subarray, what is the minimum? Minimum value is 1. What is the maximum value? 10. If the distance between minimum and max is greater than limit, that means this can't be that subarray, right? If the distance between minimum and max is less than the limit or less than or equal to the limit, that means every other element distance would always be less than equal to the limit because everything else is either less than the minimum element or less than even the maximum element, right? So you got, greater than the minimum element and less than the maximum element. So you have actually gotten the maximum distance that this subarray could have between them. Okay, so going through this route, we can easily see that we can go through each subarray and figure out the min and max for for the for the subarray starting from number from this number, then starts from this number, and then this, and keep doing it until we find the max length. So what would be the complexity of that? N square, right? You will do one loop for starting from each number, and then you will do another loop that would find a min and max, and then you will say whether to discard or take the length. Then you will start here and do the same thing, and for this, and so on. Okay. So now we have gotten to a point where we have a n-scale algorithm, okay, and we have discovered an important pattern here, which is we have to know min and max of the subarray. Okay, so we are gonna now take this and we're gonna again discard our sketch and we are gonna let's write this example. So 10, 1, 2, 4, 7, 2. Okay. So what can we do? So what we are looking is better than n square, an algorithm that is better than n square. Okay. Or basically you can say actually less than n square, right? So you want something that is less time consumption. So we are either looking for something like a log n log n or n, right? I mean those are the two options that comes to my mind. So thinking about that, uh, I one idea would be maybe can we sort this array, and that would give us at least n log n. But sorting is gonna destroy the order, right? So sorting is just not gonna be a right solution here because we need a continuous subarray. If we sort it, it would the elements have moved and we don't know which one is which element. So we are probably looking at n solution. So this is where our new our pattern comes. Okay, this pattern is called sliding window pattern. Okay, and we use two pointers along with some sliding window and maybe some other data structure also, sometimes like a hash map uh, or some array to keep counts and stuff like that. Sliding window is a pattern where you have a window, basically a left pointer which and a right pointer which we use to provide us a window. Okay, so here is our window. So the idea is you try to get to a point where your window is applying that constraint. So what is the constraint here? We are less than equal to limit. So we are gonna go through our window of left and right. So we basically have two pointers, both starts from 0 and 0, and then we keep moving right until we are no longer in our limit. We are not following our limit. Once we are not following our limit, we start moving the left pointer. Okay, so we start moving this left pointer until we again start following our constraint, which is less than equal to limit. Okay, so anytime we get greater than limit, we start moving the left pointer. Anytime we are less than equal to limit, we start moving the right pointer. This is, let's say, right pointer. Okay, so now that we understand how sliding window pattern works, we have to think about how to use it in this problem scope. Okay, so let's discard this page again so that we can go to uh, thinking about our pattern. So again, we have 10, 1, 2, 4, 7, 2 as an example, and the limit is 5. Okay, so we're going to apply our left and right pointer solution to it. We also figured out that what we are going to need is a min and max. Okay, so how do we basically find a min and max is the tricky part here, right? Now not only we want to keep a left and right pointer, we want to also keep a, in for every window. In this case, we need to also keep a min and max of that window, right? Min and max in this particular window. I'm writing at the ends, but that min and max element could be anywhere in this window. Okay, so we want to keep the track of the min and max in this window, and then we can only figure out if that min and max you know um, is applies the constraint applies to that min and max, right? If the min and max is greater than the limit, then we need to move the left pointer unless min and max again gets into the limit, and so forth and so on. Okay, so let's think about what other data structure can give us a way so that we can put some kind of elements in it such that we can easily fetch min and max. Okay, so one data structure that comes into my mind is set. Okay, so what does set does it? Set helps you keep a track of elements, but they are also, it's an ordered array, or it's an ordered data structure, a map or a set. So you can put elements, and then you can say that the first element will be the smallest in this, and the second element will be the largest in it. Okay, you can the problem here is, though, we have duplicates also, right? So you have two here, two here, right? So technically, I mean, uh, you so you have two choices here. Basically, you can either use a map where you can actually put int and a count. Okay, so that way you can only remove the element when the count goes to 0, or you can use something like a multi-set. Multi-set is very similar to set. It just allows you duplicates value to be inserted as well. Okay, set would not allow duplicate, neither would map. So since we have duplicate here, we are going to rely on multi-set in this example. So what we can do is, let's look at this again, our example, our left pointer, and so we are going to basically create. So remember, you can think about multi-set as a ordered array. Basically, I mean, you can actually store it in a vector, but then you will have to continuously sort it at every step to find min and max also. So other alternative would be to use vector also, but that would require a continuous sorting operations to find min and max in it. Okay, so we are going to use multi-set. So let's assume this is our multi-set array that we are going to draw here so that we can push the values on it. So we will keep the max values on the top here and min values here. Okay, so let's say we try to come here, and we are gonna insert 10, our left pointer, and let's say right pointer we will draw with green arrow. Okay, so there is a right pointer and there is a left pointer. Okay, so the left pointer and right pointer are pointing to the same element. At this point, what are we gonna do? We are gonna simply insert it, because left and right are pointing to the same one. There is, if you at this point, if you ask, okay, like what's the what's the element. There is nothing in your set. So there is, so it's a good idea to put, the very first element inside our set, because that's your starting point. Okay, so let's you put the, then you can move the right element. So the right goes here, and you will see the one is there. We will insert one, and at that point we will also, um, the next time we will come back, we will see, okay, what's the min and max. So min would be, at this point the min is pointing here, this is min, so min would be 1 and max would be 10. So when we will take the diff, we will get 9. We will say that's greater than 5. Okay, so that means what we have to do, we will have to move the left pointer. Okay, left pointer, we have to move the left pointer. We have to move the left pointer. So we move the left pointer, right? But what we have to do, as soon as we move the left pointer, we have to remove this element from the set. So we remove 10 from our set because we moved the left pointer. So this is our sliding window, right? Our window was this first, 10 and 1, but it did not, the constraint did not work. The constraint didn't work. Okay, so we started moving the left pointer, and our window is now back to this, right? So first time our constraint worked because there was only 10 added, 10 minus 10 was 0. We calculate our length, that happens to be the one element. Then we were trying to put two elements in the set, and we were hoping those two would fulfill the constraint. It did not, so we basically moved the left pointer, and now our window is back to only one. Now we will again start moving the right pointer. So our set would look something like number 1, number 2 element, and so your right would come here. Then we will again compare 1 and 2. Of course, we are less than, number 5, so we are all good. Keep moving the right, put 4 again. Then we will ask the set, are you, what's the min and max? 4 minus 1 is 3, we are less than 5. Then we will come here, and we will reach 7, and then we will again come back and ask, our set, what's the max and min? It would give 7 and 1, which is gonna give us number 6, and which does not satisfy our condition. What was our condition? It needs to be less than or equal to 5. So what we are going to do now is we're going to start moving. So our right pointer has moved here now. Okay, our left pointer was still here, right? Our left pointer was still here, right? Now we're going to start moving left. So we're going to remove 1, and we're going to check, can we, is the min and max in the range? 7 and 2. Yep, it's in the range. All good. So no problem. Now we are going to move right. So at this point, our right pointer has reached the end, and that's where our equation, and that's, you have already reached, your right pointer has reached the end of the array, so you can't really, get max of that. The max length is gonna be whatever, wherever the left was at, and the right, when the right is at the end. Okay, so at this point you can easily see, of course we will also check if when the right reaches the end, we will check if there is the distance between the min and max is less than or equal to 5. In this case it is, hence the length was this subarray, or length was 4. Okay, so this is all about sliding window. Usually when you're using sliding window algorithm, sorry, you have to use some other data structure like a map to maintain a count. For example, in this also case, you could have maintained a, like an ordered map, and put a count with every element, and then decrease the count and only remove it when the element goes away. So you can either use maps, multi-set, and, or array, or some other data structure usually needs to be used to check the constraint. Sometimes it's just two numbers also. You like min number and max number. So, right. So now I think now it's a good time for us to start trying to write a code for this. So we are going to try to code this. We'll see how it goes. Okay, let's see. So we already know that we will need what we are going to need. Let me move. We are going to need a left and a right pointer. Okay, so because we discussed that, so we're going to put int leftPtr both starts at 0, rightPtr both starts at 0. We also figure out that we will need something like a multi-set. So we're going to create a multi-set here. We're going to call this, let's say S, it doesn't matter. Okay. So now you have a multi-set and you had this. So you can always assume, as long as your limit, since limit is less than equal to 0, you can always assume as long as your array has something. Again, the constraint says that the array has at least one element. So you can always say your max size is gonna be 1, right? So once you know that, you can now say, okay, what we can do is you can start moving the right pointer until rightPtr until you are less than nums.size, right? That's what we said. Gonna move until rightPtr is less than nums.size. Now, what are we gonna do at this point? First of all, since our so we can basically do one thing here. We can say we have to find our diff between the min and max element. But since set would be empty the very first time, you are not going to be able to find anything. So we can say if s dot size equal 0, then you can say, like, you can declare something diff here, and you can say diff is 0. And if size is greater than actually 0, let's say, you can say your diff is going to be, you find your diff. How do you find your diff? In case of set, you can do absolute between like a max, which is going to be, I think you can get, I think you can get s dot end negative negative, right? Oh, sorry, I think you have to put it on the iterator like this. So that should give you the first element or the max element, and then you can also do the same thing for the first element, that is s dot begin. Okay, so now you got the begin element and the last element this way, and you don't really need even absolute, right? Because you always get the big element. Okay. Yep, that should, so that would be your diff. Now you can say, now what we need to do is we need to move our rightPtr. So we're going to say rightPtr we definitely need to move. So we're going to just write that first. We're going to also say if our rightPtr, if we are actually, if our diff is actually less than or equal to limit, right? And or that's pretty much what our condition looks like, and we can say then what is going to be our max length, so or max size, right? So we can say max size is going to be max of max size, right? um, and right ptr minus left ptr plus 1, right? So that's going to be your max size in that case, right? But what we haven't measured yet is, and we also need to insert, um, we need to insert the element at this point in our set, and we're gonna say insert the the nums at, let's say, right ptr, right? So this will get you the number at right ptr, and this will give you the max size at that point, right? I mean, let's move it actually here so that we put it just before, right? So all set. And now if the problem is, what could happen is, what we discussed was the right ptr might your diff might be not apply, not would not be inside this condition less than equal to limit. So let's say while diff is greater than limit, so if the diff is greater than limit, what do? We basically start moving the left ptr, right? So we're gonna say, we're gonna but before moving even left ptr, we're gonna erase that element because now our window is getting thinner. Okay, so we will say left ptr erase and left ptr plus plus. Okay, so for the right one we are inserting it, for the left one we are simply erasing it. Okay, and we can also say here, do it only until leftPtr is of course nums dot less than nums dot size, right? So we are squeezing the window here, and we are saying if diff is less than equal to limit, and keep inserting. So we keep inserting stuff into it. We keep calculating the diffs, and here we are saying diff until the diff is greater than limit. You erase it, but another thing we would need to do is also update our diff, right? So we will say same condition here. After erase, we will say if s dot size is greater than 0, diff is gonna be this. Um, so yeah, so that should be fine, I would think. And return max size. Okay, so let's try running this. Oops, that didn't work. Let's see what we did. So I think something is wrong, right? So let's see. Um, so if we look closely, this last condition where we are incrementing the right PTR, and so I see two problems here, right? One is we are incrementing the right PTR and inserting the element just before that. That means this element, the line 32 element, might not participate when we are doing this diff. And if we look carefully, that's why we have this even check. So how about we move this here? Sorry, not this. The insert. So the very first thing we should do in our set is we need to insert it. Okay. This way we will not have this problem of checking the size at all. We can simply get rid of it, and we can put this here and remove this. Okay, cool. And now we can do this diff here. The second problem is this erase. The erase is gonna erase everything. So we can't every entry of this. We can't rely on this. So we need to erase only uh, only the one of them. So we need to find that value, and that gives us an iterator, and we erase that iterators only, right? So until the size is greater than 0, I mean, it does not really matter if there is empty, it's gonna hopefully give us, so this should never get empty now. And we can keep increasing our left PTR. Okay, so this is right. And then now this should, we don't need insert here, so we can remove it because, and then we are going to the next location. So we start from whatever our location is, we insert that element, we figure out diff. Of course, the very first time the diff would be 0 because both are the same element. So we will do 0 minus 0 plus 1. That's going to become our max size. And then we are going to increase our right PTR, right? And then we're going to insert that. And then we are going to figure out whether we need to move left or not. And then we're going to do that. I think this should work. Sure, let's try submitting. Yep, that works. So that was the problem, I guess. I hope you guys enjoyed it. Thank you. Thanks for watching.